Okay, so there's one other topic we need to talk about with respect to this molecular geometry, and that has to do with polar bonds. And so we've already talked about the polar bonds and how we can figure out if a bond is polar or not. But now we have to sort of look at the structures of the molecules and determine if they are polar or not. And unfortunately, it's not super straightforward. For the most part, if you have a polar bond, you'll have a polar molecule, but not every single time. Okay, so a dipole moment is actually just a measure of the difference, the degree of charge separation. So in other words, if you have a positive charge and a negative charge, let's get this. It's the degree of charge separation in a molecule. So a polar bond is a dipole moment. Now a dipole moment actually is a vector. So usually what we see is it kind of pulls toward the negative end. So a vector, you can think of the positive end here, and it pulls toward the negative end. Now, what is a vector? Some of you may know a vector. A vector has both amount, so the distance, so like, here's a small vector and here's a large vector. They have amount, but they also have direction. And so if you've ever taken some math with vectors, you know that if they're going in the same direction, you can add them together. So these two add up to the third one. But if they go opposite each other, they cancel each other out. If they're the same, the same magnitude but different directions, or if they kind of go in different directions, then the sum of them will be kind of in the middle. So anyway, that's what a vector is. And polar bonds are considered vectors. So if we look, for example, at carbon dioxide, we know that a carbon-oxygen bond is polar because we've already calculated that. A carbon is 2.5, oxygen is 3.5. The difference between them is 1.0, so this is a polar bond. And we know that the oxygen is more negative, so this end is more negative. But then the bond on this side is also negative. Is polar, and the oxygen is negative and the carbon is positive. So it's a vector. So we have a vector pulling in that direction, and we have a vector equal and pulling in the opposite direction. So what happens is they cancel each other out. And so this molecule, even though that it has polar bonds, actually has a zero dipole moment, meaning so if it's symmetrical and the vectors cancel each out, it's considered nonpolar. Now this molecule also has polar bonds. So a nitrogen-hydrogen bond is polar. Nitrogen is 3.0, hydrogen is 2.1, so the difference is 0.9, and so that is a polar bond. And each of these bonds, now they always go from the positive to the negative, so there's one pulling that way, the nitrogen's pulling up, but there's nothing over here balancing it out. And so overall, this has a dipole moment where the top is more negative and the bottom is more positive. Because it's not symmetric and there's four different bonds, or well, there's four domains. Three of them are bonds that are all vectors, but the fourth one is not. So there's not something balancing it. So overall, this has a vector in this direction. So it's pulling up, and one end of the molecule is polar. So not only do bonds have polar ends, positive and negative ends, but molecules overall can have positive and negative ends. So this molecule is considered polar. In the same way, water can also be considered polar. So, if we've got water molecules, I showed you this a little bit earlier. So we've got this way. Oops, nope, it's the other way. It's always pulling from the positive to the negative. So similar, you've got one going to the left and up, one going to the right and up. So overall, if you were to add these two vectors, I didn't draw that very well. Let's try that one more time. So overall, it kind of does this, where this end is negative and this end is positive. And so it's a sum of vectors. So the reason why, and remember, water is bent because of the unshared pair. So there's nothing coming from the other way to balance out these vectors. And so that's why the molecule is polar. So that's why I said earlier, for the most part, if you see a polar bond, most of the time, then the molecule is also polar. Of course, here, so here's some other examples. Chlorine, hydrogen, since it's just a single bond, then clearly if it's a polar bond, then the molecule is polar. So again, chlorine is a 3.0 and hydrogen is a 2.1, so the difference is 0.9. So we know this is a polar bond. We can actually draw it in that direction. So this is a polar molecule because it's just one bond, and so it has to be polar. Now if we look at this bond here, so carbon hydrogen we said is really nonpolar. However, the only polar bond we have here is carbon to chlorine. Chlorine is more negative than carbon. And so it's polar in that direction, but these don't cancel out because they're not the same kind of bond. So overall, we have a positive end and a negative end, and this is a polar molecule. If we look up here, this is also tetrahedral, but now this time, because all four of the bonds are identical, again, now we have canceling out. So if they're all four going in every direction, and again, it's not the best, it's harder to see in 2 dimensions, but if you saw it in 3 dimensions, you know they would be equal and opposite, and they'd be canceling other out. So overall, we call this a nonpolar molecule. There's no, one end is not more negative than the other. And then I already just showed you this on the other slide. So again, we've got the HO, but because we have the unshared pairs this way, and they're not being balanced out in this way, then the overall polar bond is this way, and we have the positive end and the negative end. So so that's the last thing you're gonna have to do is, so first we do the Lewis structure, then we figure out what the domain geometry is, and then we figure out what the molecular geometry is, and then we have to determine if the bond is polar, or if the molecule is polar or not polar. So what do we need to look for? So you can see here that most of the time it's polar, but not always. So here's kind of a guideline for determining if a molecule is polar or not. So the first thing you want to do is say, okay, let's look at all the bonds in question and let's determine if any of them are polar. Because here's the thing, if you don't have any polar bonds at all, then the molecule can't be polar. So if the answer is no, and let me just give you a little heads up, don't just check one bond. If there's different types of bonds, make sure to check them all, especially if the first one you check is nonpolar. Like that last example, the carbon-hydrogen bond was nonpolar, but the carbon-chlorine bond was. So you want to check all the different kinds to see if there's a polar bond or nonpolar bond. So if you have no polar bonds at all, then you're done. Your molecule's nonpolar, and you don't have to worry. However, if there are any polar bonds of any kind, then move on to question number 2. Question 2 says, are all of the attachments identical? And when we say attachment, that means each electron domain. So this will include any unshared pairs. So the best answer is if there's 4 domains, are all 4 of them identical? Are there 5 domains? Are all 5 of them identical? If there's 2 domains, are they both identical, and so forth? So unshared pairs would not be identical to a bond. So in those last examples that we looked at, there were some bonds and some unshared pairs, so those would not be considered identical. So if all of them are identical, like on the last slide, all 4 chlorines were identical, they canceled out. The carbon dioxide, the 2 carbon oxygens were identical, so they canceled out. So if they're all identical, no, then the molecule is polar. So if they're not all identical, the molecule is polar. So as long as there's a polar bond and they're not all identical, the molecule is polar. But if they're all identical, the molecule is considered nonpolar because all the dipoles cancel each other out. So we did look at a few examples, and I think I have a few more examples here. Okay, so let's predict if the following molecules are polar or nonpolar. Okay, BRF. Well, this one should be pretty easy because it's just a single bond. So the electronegativity for Br is 2.8, F is 4.0. The difference between them is 1.2. So yes, there is a polar bond. Since there's only one bond, then the molecule has to be polar. So this is a polar molecule, polar bond and polar molecule. Okay, SF6. Well, here's SF6. So there's 6 F's bonded to the S, and you can almost see that it is symmetrical, so you can pretty much guess that it's nonpolar. But let's go through the steps. So first, let's look for polar bonds, because I may ask you that, even if the overall thing is. So let's look at the bond. The only kind of bond we have here is an SF bond, and here's the electronegativities. So S is 2.5, F is 4.0, so that's 1.5, so that is a polar bond. So definitely you have polar bonds, but because the molecular geometry is octahedral and all 6 attachments are identical to each other, the molecule's nonpolar. Let's see, one more example. All right, SO2. So first of all, well, let's look at the picture. Okay, so first of all, the difference between S and O is 1.0. So there are polar bonds. Yes, there are polar bonds. So now here we look at the molecule. So this is a polar bond, and this is a polar bond. All right, but so let's decide. So we definitely have a polar bond, but now we need to think about the geometry. So this molecule has 3 domains. Now the two bonds are considered equal because of the resonance structure. The 2 bonds are both about 1.5. So the bonds are considered identical because they're both bonded to the same element. But because there's an unshared pair here, all 3 domains are not. So there's 3 domains. They're not all the same. So so they don't cancel out. So if you have a polar bond, you have a polar molecule. So yes, polar bonds and 3 domains. Not all 3 domains are identical. So they don't cancel each other out. So the molecule is considered polar. So we've just got a few other topics to kind of little topics here and there to kind of tie up. So bond length and bond order. First of all, bond length should be fairly easy to understand. The bond length or bond distance is just the distance between the 2 atoms in a bond. So it really would be between the nuclei of one atom and the nuclei of the next. So from the center of one atom to the center of the other atom. One thing you can do is you can actually look up, there are bond lengths for elements. So if you know knowing the bond length in a molecule can sometimes give clues as to the type of bonding, but how do you do it? We can look up covalent radii. Radii for our values are assigned for every atom, atoms A and B, and if you add the radii together, then you get the bond length. So here's what we see. So again, if you have, let's go from the center. So if you go from the center, you've got the radii of the carbon atom, and then you have the radii of the chlorine atom, and if you add them together, then you get the bond length, which is the 2 radii together. So we can look these up on tables. Here's guys, very tiny. I see table 9.4 has a lot of them, but if we want to know the carbon, so carbon's here 76 picometers, and then the chlorine, I guess they're in numerical order of atomic number. So chlorine is where is it? Chlorine is 17. So 102. So 76 plus 102 would be 178, and the amount is picometers. Now, it's not super interesting to know the length, but sometimes it's important to know that. Probably more important, though, is to know the bond order. And the bond order is just it's determined by the Lewis structure, and it's actually how many pairs of electrons are in a bond. So bond order, so it's really easy. Bond order is just what kind of bond do you have. So so bond order is if it's a single bond, it's first order. If it's double bond, it's second order, and if it's a triple bond, it's third order. Now let's look at what happens with a bond. So in fact, if you have a multiple bond, the radii changes a little bit, or the diameter changes a little bit. So bond length actually decreases slightly as you get from a single to a double to a triple bond. So bond order increases, bond length decreases. What about bond energy? The bond energy is how much energy it will take to break the bond. Energy needed to break the bond. And so it should make sense to break bond. So it should make sense that a single bond would be easier to break and a triple bond would be the hardest. So bond energy increases, bond length decreases. So as you go from a single to a double to a triple bond, you're getting shorter and stronger. Kind of, you could sort of think of it as a rubber band. If you've got one rubber band, if you put a second rubber band, it'll get a little closer and tighter, and a third rubber band will get even tighter and closer. All right, so let's do a cumulative. There's some little brackets down here, but you'll see where they came from in a second. Let's do a cumulative example, and this will kind of bring in together a bunch of the things that we've been talking about. Question is, which is predicted to have a shorter SO bond, an SO3 molecule or an SO3 -2 ion? So let's draw each of them. Okay, SO3, no negative charge, sulfur trioxide. Okay, so there are six valence electrons plus another 18, so there's 24 electrons. So if we draw the Lewis structure, here's what we get. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've used up all of our electrons, and sulfur here still in the middle needs 2 more. So a double bond is necessary, and this is one of those situations. So here's what I was talking about before. Which one do you pick to do a double bond? Well, since they're all identical, what you need to do is draw the structure 3 times, once with the double bond going to each oxygen in turn. So it looks like this. So first I drew the double bond to this oxygen. Don't forget to remove those electrons because the double bond is what they're sharing 4 electrons now. And then I drew it to the center oxygen, and then I drew it to the left oxygen. So this is a resonance structure. Now, what does that mean? Technically speaking, each bond is approximately 1 1/3 because that double bond is sort of shared by all 3 oxygen. So the bond order in this case is about 1 1/3. Even though technically it's a 2 singles and a double, but they're all equal, and so they're really about 1 1/3. All right, now let's draw SO3 -2, and you can almost probably see where it's going because we're missing those 2 electrons on the sulfur. So if we have 2 more electrons, if we have those 2 extra electrons from the ion, then we see that the extra electrons are able to just go right there on the sulfur. So now sulfur has 8 electrons. They all have 8 electrons, and now you can sort of see why SO3 is a really common ion. A -2 is the common ion because it adds those 2 ions. So no double bond is necessary. So what's the bond order for this one? The bond order is 1. So obviously the SO3 without the -2 has a bond order of 1 1/3. This has a bond order of 1, and they're asking which one has the shorter bonds. So the SO3 neutral will have the shorter bonds because they have a bond order of 1 1/3, whereas this is just a bond order of 1. Which one is a stronger bond? Also the SO3 without the -2 charge, because it has they'd be slightly shorter and slightly stronger. Okay.